So now we've got kind of a hodgepodge of random pieces that accumulate that we need to evaluate as far as stabilities. We talked about ion stabilities already when we were dealing with carbocations from mass spec. So in theory, you should be able to go through and decide which of these is the most stable. Okay, zeroary, primary, secondary, or tertiary as far as the anions go. So I'll give you a sec to think about it and pause if you want longer. If we go through and evaluate these are all reactive because of that negative charge, which means they have excess electrons. Okay? If we have excess electrons, the way we make it less reactive to make it more neutral, okay, is to remove those electrons. Well, we can't remove them, so we need to make sure there's less electrons nearby. Okay, so when we go through and evaluate hydrogen, depending on how you want to count this out, or sorry, let's not look at hydrogen first, we could move to the bonds nearby. When we go through and look, all of our structures have the same 3 bonds, which means they all have 6 electrons coming out there. Because they're all the same, just ignore it. We won't worry about those because they aren't having an effect on our overall chemistry. As we move further out, we can then see we'd move out to hydrogens in the zeroary, or hydrogens versus carbon in the case of the primary. So again, we can use selective vision and we can ignore the 2 hydrogens because they aren't different. The difference lies in the hydrogen versus carbon. Hydrogen versus carbon, what's our difference? Well, the number of electrons. Carbon came in with 6 total electrons. Hydrogen comes in with 1. Hydrogen's 1 electron is in the bond, so that's already accounted for. Carbon came in with 6. 1 of them is in the bond. The remainder are now floating around somewhere near outside it. So if we go through and evaluate, the primary has 5 extra electrons around that anion than the zeroary. What does that mean? That makes this one, our zeroary, more stable because there's less electrons around it. Okay? If we move down to the next one, primary versus secondary, and we count it out, we see that same carbon again, so we can ignore that now from our argument. We had that hydrogen, which was the same. We can ignore that. We're now looking at a carbon versus a hydrogen again. Again, 5 extra electrons. Okay, so we've added more electrons on top of what we already had, which makes the primary more stable than the secondary. And what we'll find is that as we move through this, the least stable ends up being the tertiary, and the most stable is the zeroary, or officially the methyl, okay, anion. What we're trying to do is evaluate those differences. We're technically still using the same rule set that we evaluated before. What was that rule set again? Charge, size, electronegativity, resonance, induction, okay, and then, oh crap. Well, charge, they're all the same charge, so irrelevant. Size, these are atom effects here. They're all carbon, so irrelevant. Electronegativity, all the same, so irrelevant. Resonance, we don't have a large enough structure to evaluate resonance, so we're going to remove that. Induction, is there a difference in electronegativity between hydrogen and carbon? It's so insignificant that we call that a nonpolar bond, so that's not relevant. And we're now into this, oh crap, well, we have to be very careful now in evaluating that. Okay, so in this case, what we're calling this is a substitution effect, or what I'm calling it is a substitution effect. By substituting things on there other than hydrogen, it changes the stability. Okay, and you'll note that we have to change our perspective on more or less stable depending on what species we're looking at. In this case, we're looking at anions. So the least stable ends up being the tertiary based off of the substitution. Okay? But as we talked about when we looked at mass spec, we also have radicals and cations. And if we move over to the cations, if we try and just say, well, it's the same thing, it must be this one being the most stable, we have to be careful because we're now looking at a positive charge versus a negative charge. Those are opposites. Okay? So to a first blush, you should immediately be saying the bottom one should be the most stable because we have the opposite definition rolling in this case. Okay? And indeed, it ends up being true. Okay? And again, we're still using substitution to explain it, but we're explaining it in a slightly different pattern because we're looking at cations versus anions. Okay? These are looking at kind of one-off states. We're going to have to see how these one-off positions will affect us moving forward, and we'll see that kind of in the, not in the next few slides, but hopefully in a little bit. Okay? So, still on the ions, you'll see this concept known as the zwitterion. Zwitter is, I believe, German for twin. So if you look at a molecule that has two charges in it, one being positive and one being negative, that species is known as a zwitterion. Okay, so this guy right here is a zwitterion because it has both the positive and the negative in it. Okay, these molecules can become vastly more complicated, and that's what this slide is actually referencing, because you now have two different sites of reactivity. You've got the positive charge reacting at one end and the negative charge reacting at the other, which means both of those chemistries are at play when you have to consider how they react. The concept of this, when we're talking about acids and bases, comes in full force, brutal, painful analogies when dealing with biochemistry and the charge on an individual protein or an amino acid. Okay? To those levels, you usually end up memorizing rule sets to cheat your way through it, which is okay, but the underpinnings of that are all your Henderson-Hasselbalch expression. Don't stress about it here. I want you to just be aware of that concept. Okay? Chapter 7. We don't talk a whole lot about Chapter 7 because it's in that play pause it video that I asked you to go through and watch. What this chapter really does is it goes through and breaks down the individual pieces for our reactions, and in particular the mechanistic pieces. This slide is popping up because there's a question in the smart work about electron rich versus electron poor, and it can become difficult to associate those things when we go through and look at individual reactions. So what we're concerned about is those electronegativity differences and trying to decide electron rich versus electron poor. Okay? So electron rich, there tend to be electron donors, which makes them negatively charged. Lewis bases, Bronsted bases, and nucleophiles are all electron rich. They're all typically elements that have very high electronegativities. Okay? Electron poor are now the opposite. They're electron acceptors, they're positively charged Lewis acids, Bronsted acids, electrophiles, typically low electronegativity, and non-metal to a more electronegative non-metal. Okay? Which is going to bring in the next question. If I asked you to identify NaCl, okay, as electron rich or electron poor, how might you do it? Okay? Well, one option, you'd say, well, electron rich, the chloride fits in the electron rich, the sodium chloride, or the sodium fits in the electron poor. So it has both, so which one is it? Well, it turns out this one is just really going to be referenced as electron rich. There are a couple answers that are all kind of hand-wavy and a bit obnoxious to deal with, but let's work through those explanations. What do you know about the sodium ion? As a hint, push you to Chem 151, first semester general chemistry. As a secondary hint, we could write DR for double replacement. And as a last hint, we could move to our solubility rules. When we look at our solubility rules, sodium ions, or anything with sodium, is soluble. Sodium ions act as spectator ions, which means they effectively disappear from an argument. Okay? It is there to ensure that we see the chloride comes in as a negative charge. Since the sodium has disappeared from the argument, there's no longer an electron-poor atom. All we're looking at is an electron-rich atom. Okay? That's not a particularly fun way to do it, but it's true. The other thing that we could do is actually follow where that arrow is pointing we're referencing a nonmetal to a more electronegative, well, this is more electronegative, sodium to chloride, nonmetal. Sodium is a metal, not a nonmetal. Okay? So our metals effectively just kind of fall out of our analysis. We're really only referencing the nonmetals as electron rich and electron poor. Okay, so try to ignore the metals. Doesn't necessarily make it easy, but it can help you to classify. If you can identify an electron rich atom, you now know potential reactivity. It could act as a Bronsted-Lowry base or a nucleophile. If you identify an electron poor atom or molecule, you now have the potential reactivity for a Bronsted-Lowry acid or an electrophile. Okay? And that can simplify your analysis, which is one of the reasons why I asked that question in the smart work, even though it's a bit challenging to get through. Chapter 7 does bring in another intermediate. Okay, this is an intermediate that will haunt you through your entire OChem career and biochem career if you have to take biochem. You're talking about the ketoenol. Keto for the ketone. So if we go through and take a look at our structures here, we have a carbon double bonded to an oxygen. I know we haven't specified this piece out here, but it is typically some type of carbon. It's certainly not an oxygen. Okay, so we're looking at carbon or hydrogen, which means that functional group that we're looking at in red is largely a ketone. So that's where the keto part of our intermediate comes from. Now let's take a look at the other part, okay, or the other structure. We have that alkene, a carbon-carbon pi bond, which makes it an alkene. The remainder of the name becomes a little bit tricky because what we're looking at is the basic form of this. Okay, but if I added a hydrogen up here, what functional group do I now have? And I don't like it being in red. Well, now I would have an alcohol. If we get creative, just like I did with my name, we delete the alk, and we would now have an enol. So when we're talking about the ketoenol tautomerization, we're referencing the different pieces of those functional groups. The ketone is related to or tied to an alkene that is close enough to an alcohol to now warrant the need for a new functional group name, the enol. Okay? Why does this become important to us? Well, if we go through and take a look at a ketone, we can potentially remove a hydrogen. Sorry, let's draw the ketone. I could have a base come in and remove that hydrogen, thereby placing the electrons on the carbon. Okay, so we would get that negative carbon. For those people saying that a carbon-hydrogen bond is nonpolar and that a base should not be able to deprotonate that, you would typically be right. This is why ketone chemistry becomes tricky. What is available to that lone pair electron? Our favorite 9-letter word, actually let's count it out. We have resonance. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 letters. Hopefully I remember that for the rest of the semester. So that resonance stabilizes that negatively charged carbon, so much so because we're now putting the negative charge on an oxygen. Okay? Why does this become important to us? Well, once I've removed that hydrogen, I now have this structure, this stabilized structure, okay, which is oftentimes referred to as the enolate anion. Why the enolate? Because which of these two forms is the most stable? Okay, so here's our keto form and our enol form. Which one, if you were asked to draw a Lewis structure, would be the more stable structure to draw? Hopefully, you would jump on the enol form being the more stable because you have the negative charge found on an oxygen as opposed to on a carbon. Okay? Because that is our more stable form, that's where we're seeing reference to the enolate anion encompassing both of these. Okay? So, now I throw an acid at it. So now that I've got this structure formed, and I throw an acid at it, where does that acid react? Does it react at the negatively charged oxygen of the enol form, or does it react at the negatively charged carbon of the keto form? Okay? One argument that we might push is be like, well, does it matter? Okay? Well, to decide does it matter, what we should do is draw the products. Okay? If we place the hydrogen on the enol form, we would end up with that. If we did it to the keto form, we would end up with that. Okay, so are those structures different? Yes. Since they're different, we have to now decide which one is the preferred pathway to move. Okay, that's where we run into a bit of an issue with this and why we have to consider it. Okay, I would argue we've already kind of pushed in a very hand-wavy way, okay, so not officially true, but it works, how we know which answer we should end up with. Okay, when looking at resonance structures, where should our chemistry happen? Should it happen with the best resonance? Okay, because we have our negative charge on the oxygen, or should it happen at our first worst? Okay, well, we said first worst, so there we go. If we follow my method, when we encounter this kind of weird functional group, okay, the alkene alcohol structure, when we protonate it, we should protonate in such a way that we end with the ketone and not the enol. Okay, does that mean the enol is not relevant? No. The enol is definitely still relevant. Okay, but what the enol will do as soon as it forms is it will convert itself to the ketone. Okay, so that chemistry is going to pop up later in the semester. Those trace amounts, okay, because we see the big red X, oh, we don't have to worry about it. Those trace amounts are significant enough that we can get all sorts of weird reactions happening through the enol form because they're all equilibrium based. And if a subsequent step is irreversible, well, then what happens? I now remove this species. If this species goes down, then the equilibrium has to shift to replace it. And we can constantly siphon off all of our keto form through the enol form. Okay, so we have to be aware of that kind of equilibrium issue popping up. It's largely a second semester issue or an issue in biochemistry if your biochemistry instructor decides to call attention to it. Deciding that balance between those officially comes down to bond energy. I don't know that it's worth the trouble to dig through that, but if you want to dig into it, this is where Carty talks about that balance between them and deciding which one's the preferred form. Okay, and it really does come down to bond energy. We can look at stabilities of those resonance structures and all of those to help kind of cheat your way to the correct answer through not horribly cheating, but a decent mechanism to get us there. So, we've now covered chapter 6. I think I covered all of chapter 6. This also, here, actually I can do it this way. Yes. So, at this stage in the game, we've now covered chapter 6, which was acids and bases and energy diagrams. And because you've watched that play pause it, and the last 15 minutes, 20 minutes of this video, we've now covered 6 and chapter 7. Okay? The beginning of the slide sequence, I asked you to add curved arrows, okay, and label the type of mechanistic steps. Now what you should be able to do is to draw an energy diagram to represent this. Okay? This does get a little bit more challenging, so I'm going to recommend you take a second to pause, add your curved arrows, label your mechanistic steps, and take a stab at an energy diagram. And again, I'm going to say pause. So, we've got our arrows added to it. We've got our individual mechanistic steps labeled out. Now we want to go through and evaluate the energies for each of these. I've arbitrarily picked A as somewhat low, okay, because I just need the space for the energy diagram. Okay. Now we want to move on to B. Where should B exist in our energy diagram? Okay, so we're looking at somewhere placing it in this space. Okay, and so we could go through and evaluate these in each of these cases. So where in that space should those individual species exist? Okay. So what do you think? Should B be higher or lower in energy than substance A? Okay. I would make the argument that you should be placing B higher in energy than A. Okay. Which has questionable validity. And we'll address that here in a second. But the argument that I would use and recommend that you at least consider is that B is a charged molecule, whereas A is not charged. Okay? And it is because of that that we should place B higher in energy. That said, all acid-base reactions are exothermic, meaning B should be placed more accurately lower in energy. Okay? So depending on which analysis you want to use to explain where the energy of B is, that's what I want to see. Okay? So if I asked this, I would accept credit for both of those positions. Okay? And more than likely what I would do is also ask for you to explain your placement for that matter, B, C, D, E, and E. Okay? So I'll make sure you're considering why you're placing them where you're placing them. And as long as your explanation holds water, I'll give it to you. Okay? So why should we place B lower? It's not just that it's exothermic. It's exothermic because we're also considering the other species in this reaction, the acid. Because that acid is being placed in here, that's what's causing a massive shift in the relative energies between A and B. Because that strong acid is going to skyrocket the energy of the reactants. In this case, I'm not looking at the energy of the reactants, I'm looking at the energy of structure A, structure B, structure C, structure D, and structure E. Okay? And that's why I'm shifting that placement around. So, C. Where should we place C relative to A? Okay, well, C should be higher than A, right? Okay, well, the question would be why? C is charged. Okay, so now where should it be with respect to B? They're both charged. Should I be placing C at the same energy? Okay. No, it should be placed at a higher energy. Why should C go to a higher energy than B? Hopefully you remember your Lewis structure rules, and C is missing an octet, whereas B has full octets. Because of that octet difference, C is a higher energy than B. How about D? Okay, so one of the questions that may have popped up in those earlier sequences would be C versus D. Why on earth should we rearrange? Okay, and that question may not have popped up because you're like, well, I just have to do it because that's what's being shown. But why should it happen? Why should we do this rearrangement? The energy diagram will actually help us to answer that question. Okay, why should I rearrange? Well, where should I place the energy of D? If we evaluate our stabilities between C and D, we're looking at C being a secondary carbocation, and we're looking at D being a tertiary carbocation. The tertiary has more electrons around it, which can better stabilize that carbocation, which means D should be lower in energy than C. Why would I expect the rearrangement to happen? I'm transitioning to a lower energy structure. That lower energy structure suggests that the reaction will happen. Okay? So we can use the energy diagram to help us predict why a reaction happens. We move to E. What should happen with E? Well, we were charged in D. E is not charged, so E should be significantly lower than D, C, and B. Where is it with regards to A? Well, if we wanted this reaction to proceed with any real efficacy, it's probably lower than A. Why would it be lower than A? We're comparing Br minus ultimately to, what was the piece that left? H2O. H2O being neutral is probably more stable than the Br minus, which means our products will be lower in energy. What we've now done is drawn roughly where each of those positions are. So now what we can go through and do is add our humps behind each of these, building that all the way out. Okay? We could now ask, what is our rate limiting step? That rate limiting step is going to be dictated based off of the height of each of those activation barriers. Okay, which, depending on how we've placed things, could be challenging, but that largest jump is likely to be that first step. Why should that... sorry, not the first step. It's probably going to be our second step. Why should it be our second step? Because we're going to form that secondary carbocation loss of octet. Okay, so the difference between our first and our second is going to be challenging to differentiate. A lot of that's going to come down to where you decided to place B in that interpretation. Remember, you had both of those options. Acid-base reactions are really easy. That first step probably isn't going to drive it. It's going to be that second one, the formation of the carbocation, the loss of the octet, is going to be probably the hardest step. Whoops. Okay. And we now have an energy diagram with some approximate energy differences between those, allowing us to see how it manipulates and moves through. Okay. For the most part, we should be seeing the energy decrease. You might ask, because we see these large jumps here, why would we ever clear that activation barrier? Okay, because if we say cleared that, wouldn't it be easy to revert back? And yeah, it would be easy to revert back. But is this last step easy to revert back? Not so much. So that if we go through and actually pull in all of the equilibrium stuff that we know, I'm going to erase all the mechanism stuff up above. All of our equilibrium pieces from 152, we are probably looking at all of these being significantly in equilibrium, except for the first acid-base step, except for the last one. Okay? So while C may be higher in energy than B, I wouldn't expect a whole lot of that to form, but once it forms, that's going to favor products just, whoops, come on, let me erase. That's going to favor products. This step ends up pushing primarily towards products because we have a more stable carbocation. The last one favors universally towards products because we don't have a carbocation. So as each of these small equilibriums happens, since the last one constantly siphons stuff away, the reaction will shift to form products and not be able to reverse. This concept of reversibility will play a much larger role in second semester. We'll see it get touched on a little bit this semester, but it's relatively minor in concept. After all of that, we put it all together. We've got 6, 7, and now we really start to push into 8. Before we do that entirely, I do want to give you this summary slide that you're going to see for all of our reactions. So at the end of chapter 7, we've got all of the mechanistic steps. What these are all of our reactions. Okay, and I'm going to write that on the side here. These are all the reactions or reaction types, if I could spell, are reactions that we're responsible for. So you really get 5 reactions. Each of these reactions has different mechanistic steps on how they occur, but these are our core reactions. When we talk about first semester, you're responsible for all of these. Acids and bases we've addressed. Substitution and elimination are our next 2 chapters. Addition and radical we'll see in the last unit. Okay, the substitution and elimination are by far the biggest section and most commonly tested on. The addition is a beast of an ugly mess everywhere that I've attempted to organize, but there aren't nice ways of doing it. Okay, and so with that, I'm going to go ahead and end this video, and you can look for the start of our substitution and elimination reactions in our next video.